Good morning, ladies and gentlemen. I'm Rosemary Bartlett with the Pacific Northwest National Laboratory, and I'd like to welcome you to today's webcast, Standard 90.1-2004, an overview of the building envelope requirements, brought to you by the U.S. Department of Energy's Building Energy Codes program. We're very happy to have as our speaker today John Hogan with the Seattle Department of Planning and Development. Welcome, John. Please begin.
Thanks, Rose. Welcome to the third in the series of the ANSI ASHRAE IESNA Standard 90.1 seminars for the 2004 version, and today we're going to be talking about the building envelope requirements. My name is John Hogan. I've been involved in the ASHRAE process for quite a while and in code development for quite a while. I've been working with the City of Seattle on energy codes for 25 or 30 years now. And with that background, I also got involved with the ASHRAE process, have been working on Standard 90.1 for approximately 15 years. I'm a former chair of the Envelope Committee, and I've also been involved in the IECC and a former vice chair of that committee, so I know the connections between standards and codes. And right now I'm also working on ASHRAE Standard 189, which is design of high-performance green buildings. So with all that background, I'd like to share some of those experiences with you and give you some more insight into what went into ASHRAE Standard 90.1. The building envelope criteria are primarily within Chapter 5, and we'll spend the bulk of our time talking about Chapter 5. But I also wanted to mention that there are a number of appendices that have some connection to the building envelope, and let me go over those quickly for you. First of all is Appendix A. So within Chapter 5, there are some very simple prescriptive approaches where you just comply with an R value for the insulation alone. However, to allow creativity and innovation, there's an overall performance U-Factor or C-Factor or F-Factor for the assemblies. For typical assemblies, the values are listed in Appendix A. And this is a very important appendix in the document, and we will be talking about that quite a bit more as we go through the discussion here. Appendix B has the climate criteria, and for those of you working on projects in the United States, there's a climate zone map of the United States divided by counties, and that's a key thing to look at and follow for U.S. determinations. Appendix C has the methodology for using the trade-off option, the EnvStd, the envelope standard program. You don't need to worry too much about the methodology. It's been incorporated into the EnvStd software, but if you had some questions about the algorithms in that or the assumptions, you could take a look at that appendix. But we really won't be talking about that in detail. Just wanted to let you know that was there as a reference. Appendix D contains more detailed climate data. It's not really essential for the building envelope chapter. It's used more in the mechanical chapter. But it's again there if you're looking for that information. For Standard 90.1, each version when it's republished includes a number of addenda that have been incorporated. And for the 2004 version, Appendix F lists all the addenda, all the changes from the 2001 version. So if you wanted to have some sense of what those changes were, take a look at that Appendix F. We won't be talking about that more today, but that's another reference source. And finally, Appendix G. This is a methodology that's been used in a number of green building rating programs. So if you wanted to claim a certain percent energy savings beyond Standard 90.1, this establishes the baseline. Within this, it's got the baseline for the building envelope criteria. And I wanted to point out that they don't exactly match up all the time one for one with what's in Standard 90.1. So for example, if you're doing trade-offs, the baseline for the wall assembly is a steel stud wall. So it doesn't matter if your proposed design is a mass wall, concrete block, something like that. You start with steel stud as the baseline for performance calculations. This is also another reference for you to be aware that there are envelope criteria in that. Now let's move ahead to Chapter 5. Within Chapter 5, it's got a similar outline as the other chapters. General material in Section 5.1. 5.2 outlines the compliance path. And essentially, you have to comply with all the mandatory provisions in Section 5.4. And then you can choose whether you want to comply with either 5.5, the prescriptive envelope option, or 5.6, which is the trade-off option. And finally, there's sections 5.7 and 5.8, which have the submittals and product information requirements. These are referred to in section 5.4, so in effect these become mandatory provisions. And as we go through, I'll be citing different paragraphs from those sections so that you're aware of those. Now let's move into the general requirements. And looking in section 5.1, a couple of items here. First of all, there's 3 different categories, space conditioning categories. There's non-residential conditioned space, residential conditioned space, and semi-heated space. But to talk about the residential conditioned space first, it includes categories that you'd think of as building code residential categories. Group R occupancy is a term that's used in the building code. So it's these spaces used primarily for living and sleeping. So for example, it's dwelling units, hotel, motel, guest rooms. But I also want you to be aware that this includes other areas, for example, like nursing rooms, homes, patient rooms in hospitals, prisons. These are items or areas that might be considered Group I, more of an institutional occupancy in the building code. But from a thermal point of view, they're similar to dwelling units, and so they're all considered residential. So therefore, the non-residential becomes all the other categories, which are not residential. And then there's a semi-heated space category, which might be used occasionally for warehouse type of buildings. This is a space that's heated by a heating system whose output is greater than or equal to 3.4 BTUs per square foot of floor area, but is not a conditioned space, so it's got to be below the conditioned space threshold. Now let's talk some about conditioned space. So conditioned space does not mean air conditioned. It's a cooled space, a heated space, or an indirectly conditioned space. And these definitions are from Chapter 3, Section 3.2. When you're going through the document, here's a tip. Whenever you see a word in italics, that means that it's defined somewhere in Chapter 3. So flip to Chapter 3 and you can get more detailed information about what that term means and what it encompasses. Now, cooled space is any enclosed space within a building that's cooled by a cooling system with a sensible output capacity exceeding 5 BTUs per square foot of floor area. So it's about 1.5 watts per square foot. But the key things here is it does not refer to design loads. This refers specifically to the output capacity of the equipment. So it's meant to be something very easy for designers, plans examiners, inspectors to check. You simply take the capacity of the equipment, you divide it by the square footage that it's serving, and you can see whether or not you're over the 5 BTUs per square foot. Similarly, for heated space, it's heated space within the building heated by a system whose output capacity is greater than the values in Table 3.1. For heated space, the values vary by climate zone, ranging from about 5 BTUs per square foot for the mildest climates up to 25 for northern Alaska. So it's, again, about 1.5 watts per square foot, the heating capacity. So as an overview here, it really turns out that very few spaces qualify as semi-heated. If you think about the warehouse type spaces, usually if they're uninsulated, they need quite a bit more heating capacity. Actually, for my study in Seattle, we took a look at some calculations. There were some warehouses uninsulated with, warehouse doors that were not insulated, had a heating load of about 70 BTUs per square foot. Office space is more in the range of 15. So what people were calling semi-heated spaces actually had a peak heating load 5 times as much as the fully insulated and fully heated spaces, even though the semi-heated spaces were only being heated to 50 and the fully heated spaces were being heated to 70. So again, relatively few are going to fall into that semi-heated space category. Now here's a particular issue that's related to compliance. So there's an assumption in 5122 that all the space is conditioned space. And let me quote the language here. Spaces shall be assumed to be conditioned and shall comply with the requirements for conditioned space at the time of construction, regardless of whether mechanical or electrical equipment is included in the building permit application or installed at that time. The challenge here, what we've tried to do is address this issue of non-compliance in speculative buildings. So we've had people put up shell buildings like warehouse and said, well, I didn't put any equipment in it, and so therefore it's not heated, it's not cooled, and whenever I find the tenant, then they'll fit it out and they'll take care of those costs. And it's very problematic because it's difficult to track those through the construction process, and it's also much more expensive to insulate these structures later on after all the scaffolding's been removed. So the time to do the insulation is at the time of construction. There is an exception, places approved by the building official. One example might be lumber storage. So the structure is really providing weather protection. It's not heating or cooling the space at all. Now let's move on to climate. So within the climate for the U.S., it's pretty easy to find your climate as long as you know the county. We'll take a look at the figure B1 in a minute, which shows the 8 different climate zones for the United States. If you're doing a project in Canada or an international location, for Canada you can use Table B2 in Appendix B. For international cities that are listed, you can use Table B3. And for locations that are not listed, you can use Table B4, which has general climate criteria. Now as we move ahead and we'll talk about the requirements for different assemblies, I'm going to refer to the criteria for Climate Zone 5, just to give you a sense of what the criteria are. And Climate Zone 5, starting in the Northeast, includes places like Boston, and then as we move west, Pittsburgh, then Chicago, west to Omaha and Denver, down a bit to Flagstaff in Arizona, and then up to Reno, and then to Vancouver, British Columbia. So here's the map, and within this map I'm just going to quickly talk about the climate zones. Climate Zone 1 is the mildest, and you see that's only the very southern tip of Florida around Miami. Climate Zone 2 is the Gulf Coast, and it does include a portion of southern Arizona. Climate Zone 3 is southeast and south central U.S., and also much of California, where the population lives. Climate Zone 4 starts in the middle Atlantic around Washington, D.C., going west through Kentucky, dipping down into Arizona and New Mexico, but then going up into the northwest, the maritime marine coast there in Washington and Oregon. Climate Zone 5, as I mentioned, is the one I'm going to highlight the criteria on this discussion today. Starts in the northeast, goes across to the west, dipping through Arizona, New Mexico, up through Nevada. Climate Zone 6 is northern New England, New York, much of the northern tier of the United States. The extreme northern portion of the continental U.S. is Climate Zone 7, so northern North Dakota, Wisconsin, Minnesota. It also includes a couple of areas in the Rockies in Wyoming, Colorado. Climate Zone 7 includes southern Alaska, and then Climate Zone 8 is all the northern half of Alaska. So let's start to move into the specific requirements here. First, to talk about the mandatory provisions, there's 3 different sections: insulation in 541, fenestration and doors 542, and air leakage in 543. I think you'll understand the connections better if I talk about the insulation and fenestration when we go through the specific prescriptive requirements. 541 refers to 581, and 542 refers to 582. So you'll see both of those mentioned. But I'll talk about the air leakage requirements now. And as a reminder, these are mandatory provisions, so you always have to comply with these, regardless of whether you're using the prescriptive or the target approach, or how great the energy savings are in your project. For air leakage, there's 4 different criteria in 543. The first section requires that you seal the building envelope. Seal or caulk, gasket, weather stripping, somehow you take care of all the openings. The second section, 5432, for fenestration and doors, sets maximum air leakage requirements. So less than 1 CFM per square foot for all glazed swing doors and revolving doors, and for other products, it's less than 0.4 CFM per square feet. For loading docks, there's a requirement to have weather seals to limit the air leakage when the truck is backed up against the door and they're unloading the supplies. This requirement applies in climate zones 4 to 8, so not the mildest climates. And lastly, there's a requirement for vestibules in section 5.4.3.4. Generally, this applies in buildings that are greater than 4 stories and in climate zones 3 to 8. So not the low-rise buildings and not the buildings in the warmest climates. There are some exceptions for small spaces, small retail spaces, for example, and for revolving doors. I will note, though, that in 90.1-2007, these criteria will become more stringent. And as we go through the discussion today, I'm also going to try and highlight for you some of the changes coming up in the 2007 version. The ASHRAE Board of Directors has already made the final decisions on what will be in that document. Now they're getting it typeset. They're completing the user manual. That should be out by the end of the summer this year. Let's move on to the prescriptive option. So this is section 5.5. Within this, there are 2 general categories, opaque assemblies and fenestration. Fenestration being windows, doors, or glazed doors and skylights. Within the opaque assemblies, there's 6 different types. 3 roofs, 4 above-grade walls, a below-grade wall category, 3 types of floors over unconditioned space, 2 types of slab-on-grade floors, and 2 types of opaque doors. For fenestration, there's 2 types of vertical glazing, but this is going to change significantly for 2007, where there will be 4 different category types, and 3 types of skylights. Before we get into the criteria, the specific R values, let me give you the general requirement here. The 2 compliant options, as I referred to earlier, one is the R value of the insulation alone. So to quote, the R value is the insulation for the thermal resistance of the added insulation in framing cavities and continuous insulation only. So this does not include air films or building materials. Sometimes it is limited to continuous insulation. So when you're thinking about this, it's meant to be really easy for you as a designer or contractor, easy for the building plans reviewer, easy for the building inspector. So you're looking for the bat insulation, whatever the R value is on the bat, that's what we're talking about in the prescriptive tables here. Or if you have rigid insulation, it's whatever the R value that's on the foam here. Again, if you have some sort of innovative assembly or a different way to approach the situation, you can comply with an overall assembly U-Factor. And the U-Factors for common assembly types are listed in Normative Appendix A. And I'll give you some table references as we go along here for specific assemblies. Here's a quick picture of one of the envelope tables, and you don't need to pay attention to the specific numbers within this, but just be aware of the overall layout. So in the left-hand column tells you the type of opaque roof elements, and then there's 3 groupings of middle columns for non-residential, then residential, then semi-heated, and then within each of those 3 there's a breakdown, the U-Factors on the left, and which are maximum values, and the insulation values to the right of those, and those are minimum insulation values. Now let's start looking at the specifics. Okay, the first category for the opaque assemblies is roof with insulation above deck. We're taking the definition here from Chapter 3. First of all, it's all insulation installed above, outside of the roof structure, and continuous. So this does not apply to any assembly that has insulation inside. All the insulation must be outside the roof deck, and it's installed in a continuous manner. Now if you look over to the right, you see for Climate Zone 5 in 2004, it requires R15 CI. And CI means continuous insulation, and that's the minimum, or the U-Factor 0.063, and that is the maximum. And you see for 2007 that value is going to increase to R20 continuous insulation minimum with a maximum U-Factor of 0.48. As you're looking at roof insulation, particularly this category here, if you have a sloped roof and the insulation is continuous thickness, then you're fine. If, however, you have a flat roof and you're tapering the insulation for drainage, then be aware that these are minimum insulation values. So you need this R15 everywhere. It's not acceptable to average the R value. It doesn't give you the same thermal performance. In terms of U-factors, if you wanted to do something different, you can take a look at the assembly U-factor, the tables, Appendix A, Table A 2.2. And in terms of the insulation R values for roofs with insulation above deck, you'll notice that as you look across the climate zones, that they don't differ too much between the hottest climates and the coldest climates. Now this might seem curious, but you know that the sun is very high in the sky during the summertime, so the high R value of insulation in southern climates helps reduce the cooling loads in the summertime, whereas the high insulation R values in the northern climate is more used to keep the heat in during the winter heating season. Along these lines, and with considerations for the roofing and the cool loads, there is an exception for the milder climates that lets you reduce the insulation 10 to 20% depending on the climate zone if you have a material that meets the cool roof criteria, and that's described in 90.1. The second roof category is the metal building roof category, and this is for metal that is structural, and it's the weathering service. There's no ventilated cavity underneath, and it has steel framing members. So we're not talking about something which is just a metal skin on top of another type of structure. This is something where the entire structure is metal. And if you look for 2004, the minimum insulation requirements are R19, and for 2007, there's an addenda that's under review. A couple of comments here, and now I'm going to refer back to the mandatory provisions. In section 5.8.1.2, it requires that all the insulation be full depth when you install it to comply with these prescriptive R values. However, there is an exception for metal buildings which allows the insulation to be compressed between the roof skin and the structure. This is a way that these systems are commonly installed, and so there is an allowance to do it this way, which is not to say that it's necessarily the best way to do this, and there are insulating systems for metal buildings that do not require the insulation be compressed, but it is allowed to compress it. Again, here, if you don't want to comply with the R19, you can look at the U-factors in Appendix A, Table A 2.3. And also here, there's a similar exception for mild climates for the cool roof. The third and last type of roof category is attic and all other roofs. And it's meant to be attics, but it's a catch-all category which includes anything that hasn't come into the first two categories. And here you'll see for 2004, the minimum insulation R value is R30, and that's increasing in 2007 to go to R38 for climate zone 5. Here there are a number of specific installation requirements, mandatory provisions I wanted to highlight for you. Section 5.8.1.8 prohibits installing roof insulation on the suspended ceiling with removable ceiling tiles. So if you've got a small building that maybe looks like a house, you've probably got gypsum board up there, and so you don't have removable ceiling tiles, that's not a problem. But if you've got a more concrete frame or steel stud wall building and have the typical grid system with removable ceiling tiles, you cannot install the insulation directly on those ceiling tiles. I think we all know what happens with that. It may be installed perfectly, but after a while somebody's poking around up there, they push up the ceiling tile to work on the mechanical equipment or on the lighting. The ceiling insulation never gets back to where it was, and so you have these gaps. So it's not allowed to install it on those removable ceiling tiles. Another section, 5.8.1.6, prohibits recessing light fixtures or other elements for that matter into the insulation unless their area is less than 1% of the area. And it's a similar thing here. If you have a large area that's light fixture, it's not insulated above, you start to increase the heat loss. Just to do a quick calc on this 1%, typical 2x4 fluorescent troffer is 8 square feet. So to be under the 1%, you could only have one of those for every 800 square feet. That's 80 by 100. You're probably aware it's more difficult to see 1 per 80 square feet, so typically they may be close to 10% of the area. So this limitation is going to allow you to put a few scattered can lights in there, but not any recessed 2x4 troughers. Another mandatory provision, 5.8.1.4, requires baffles around the eave vents. So if you are blowing in attic insulation, you need to maintain the ventilation there, so have some baffles around the eave vents. If you don't want to install the R30 insulation and you have a better assembly, an alternate assembly, if you have a wood joist, you look at the tables in A2.4, and if it's steel joist, look at table A2.5. And I will note there is also a possible reduction in certain locations if you have single rafter roofs, which is where the ceiling is attached below and the roof directly above to the same rafter. Now let's go on to the different wall types. Now the first type is mass walls. And within the mass wall category here, there's a definition that it's 7 BTUs per square foot. Or if you have a lightweight mass wall, it's with a material weight of heat capacity of 5 BTUs per square foot, 4 degrees Fahrenheit, with that density of 120 pounds per cubic foot or less. For 2004, the minimum insulation requirement for Climate Zone 5 is R7.6 continuous insulation, and that's increasing in 2007 to a minimum of R11.4 continuous insulation. Now, we briefly referred to continuous insulation talking about the roof with insulation above deck, but let me talk specifically about the definition here. So taken from section 3.2, it means insulation that's continuous across all structural members without thermal bridges other than fasteners. So it's fine to glue this insulation to the mass wall, like a concrete wall or a block wall, or to have some tiny clips that attach it to the walls. However, if you have metal studs or wood studs, those are not considered fasteners. Then you must use the U-Factors. And those tables are generally, start with table A3.1a. There's more detail if you go into including the heat capacity in tables A3.1b or 3.1c. And if you have something where you're building up assemblies with wood studs or metal studs, further detail is the options contained in A3.1b. Second type of walls above grade are metal building walls, and this is similar to metal building roofs. It's the metal building type of structure, so not steel stud, but this is the entire structure is metal spanning members supported by steel structural members. You see for 2004, the minimum insulation requirement is R13. Now here a couple of things similar. The exception to 5.8.1.2 allows compression between the wall skin and the structure, and the assembly U-Factors are in table A3.2 for the metal building walls. For walls above grade, the third type, steel stud walls, it's typical steel stud walls and curtain wall systems. And here the description is a little more complicated. So for 2004, it's R13 cavity insulation plus R3.8 continuous insulation. So it's essentially the amount of insulation that you'd put in a 2x4 stud, and R3.8 is perhaps 1 inch of rigid insulation. And you see for 2007, this is going up to R13 cavity plus R7.5 continuous insulation. So that's 1.5 inches or 2 inches of rigid insulation. Now, the key thing here, metal studs, as you know if you've ever touched a metal frame window in the winter, are a great conductor of heat. And the thermal bridging is a big problem, and so you need this continuous insulation to break that thermal bridging. If you look in some of the tables at the end of Chapter 9, there's other good reference material there. Table A9.2b shows that if you install R13 insulation in a 2x4 stud, you only achieve an effective R value of R6. And it's worse as you get thicker insulation. So an R19 and a 6-inch stud only achieves R7.1 in that framing cavity layer. So what you want to do is you don't want to do really deep walls with metal studs. You do the minimum depth that you need, and then go with continuous insulation. Now the wood frame walls is typical wood stud walls, and again here the catch-all category for anything that's not in the first three types. Here the requirement is R13 cavity insulation for 2004. In 2007 this is going to R13 cavity insulation plus R3.8 continuous insulation. The wood studs are definitely better thermally than steel, but they still are not as good as the insulation. So the wood studs, for example, have an R value of about R1.25 per inch. And bats are typically R3, R3.3, R3.8, so better than the wood. So here it's also a good idea to be going with a continuous insulation. If you want to use some alternate assembly, look at the table A3.4. And I wanted to mention another one of these references. And, people sometimes think, well, as long as I buy this R value in bad insulation, it doesn't matter too much how I install it. And compressing the insulation does have a significant effect on it. So if you buy an R19 bat, but you compress it into a 2x4 stud, the effective R value is R13. So you're not getting any additional benefit. You've really wasted your money there. If you're only going to put in a 2x4 stud, you just buy the R13, don't compress an R19 into it. There's one below grade wall category, and that's the portion of the wall that is entirely below the finished grade and in contact with the ground. For 2004, you see there's no requirements here. And for 2007, there will be a minimum requirement of R7.5 continuous insulation, which is for 1.5 inches or 2 inches continuous insulation, rigid insulation. Here, similar to the mass walls, it must be continuous across the wall. If you have the metal or wood studs, then you must use the C factor. Now, the C factor is a little bit different here. The challenge with assemblies below grade are they have differing amounts of soil buffering them on the outside, and the soils have different conductivity depending on whether they're dry or moist or wet. And so as to simplify the process for designers and for compliance, all those variables are removed from the process. So we're essentially looking just at the wall assembly. We're not looking at the R values for the soil or for the air films. Now let's talk about the three types of floors over unconditioned space. So perhaps typically like a floor over a parking garage. So the mass floor, same heat capacity definition as the mass wall. For 2004, minimum R values of 8.3 continuous insulation, going up in 2007 to R10.4 continuous insulation. And here there are a couple of mandatory provisions that are specifically applicable here. For waffle slab floors, A5.2.2.3 in Appendix A requires that they be insulated either on the interior above the slab or on all exposed surfaces of the waffle. For concrete beams, A5.2.2.4 has a similar requirement depending on how deep the beams are extending below the floor slab there. If they extend more than 24 inches, you don't need to insulate more than 24 inches, but you need to insulate that first 24 inches for the beam depth. And again, if you want to look at an alternate assembly, go to Appendix A, Table A 5.2. Second type of floor over unconditioned space would be steel joist floors. So steel joist members supported by structural members. For 2004, R19 minimum insulation, 2007 going up to R30 insulation. One of the mandatory provisions, Section 5.8.1.5, requires that floor insulation be installed in substantial contact with the inside surface. So we're looking for the insulation to be pushed up against the floor. We don't want a situation where air bypasses that and you don't get the benefits of the insulation. You can look at the alternate assemblies in Table A5.3. And I wanted to point out here, you have some similar short circuiting, but it might not be as bad on the floors because usually the members have less structure connecting them. It's not like a continuous 2x4 metal stud. So if you look at Table A9.2a, shows that if you had R30 insulation, you only achieve R23.7. if it's between metal framing and 4 feet on center. The last type of floor is the wood joist floors, and again the catch-all category here for all other floor types over unconditioned space. The minimum insulation requirement for Climate Zone 5 and 2004 is R30, and that won't change in 2007. The mandatory provision here in Section 5.8.1.5, this requires that the floor insulation have these supports that are no greater than 24 inches on center. So if you have a wood joist floor and the insulation is the same thickness as the joist is deep, then it works out fine to just string some wires across the bottom of the joist to hold the insulation in place. However, if the insulation is not as thick as the joist is deep, then you need to have some other bracing inside the joist, between the joists, to make sure that the insulation is held up against the floor in substantial contact. And here the alternate assemblies are listed in Appendix A, Table A 5.4. Now there are two types of slab-on-grade floors. This is in Section 5.5.3.5. So a slab floor is one that's in contact with the ground, and it's either above grade or not more than 24 inches, 2 feet below the nearest exterior grade. If it's more than 2 feet below, then it's considered a basement, and there are no specific insulation requirements for basement floors. But if it's higher than that, two types, unheated slab and heated slab. The difference between these two is a heated slab has heating elements within the slab. So this does not refer to whether there is heating in the space. This refers to whether there is heating in the slab itself. For the unheated slab, there's no insulation requirements for a Climate Zone 5. There are some for colder climates. For the heated slab-on-grade floor, for 2004, the requirement is R10 insulation for 36 inches deep. So this is perimeter insulation. It's not a requirement to insulate under the entire slab, so certainly that would be a good idea. I think if you can imagine you've got a floor slab that's heated to 80 degrees and half the heat's going up into the space, but the other half is going down into the ground. So you're losing a lot of heat into the soil. So it would be a good idea to insulate under the entire slab, but the document does not require that. You only need the R10, which is approximately 2 inches of rigid insulation, or 36-inch depth, and that starts at the top of the slab. The last category of opaque elements are opaque doors, and these are considered all operable opening areas which are not fenestration. So swinging and roll-up doors, fire doors, access hatches, and any doors which are predominantly opaque. If they're more than half glass, they're considered fenestration. For the swinging doors, doors with hinges, and it includes revolving doors, the requirement is for a U-Factor of 0.7. For non-swinging doors, which are roll-up as well as sliding doors, the requirement is a U-Factor of 1.45 in 2004, which is essentially uninsulated, but going to an insulated door in 2007 with a U 0.50. Now there are a limited set of defaults in Appendix A7. You can also get ratings per NFRC 100 that we'll talk about in the fenestration section here for those doors. That was a summary of the opaque components. Now let's move on to fenestration. Again, just a quick look at the table. The types of assemblies are in the left-hand column, and then we move across the non-residential, residential, and semi-heated criteria. Now, I want to talk about some general requirements here before we get into the specific requirements. So fenestration, again, from Chapter 3, it's all areas, including the frames, in the building that let in light. So it's windows, but it's also plastic panels, clear stories up on the roof or skylights, any glass doors that are more than half glass, glass block walls. Essentially, if it's not an insulated roof wall or floor, then it's considered fenestration. And again, with spandrel glass, it doesn't matter what the exterior surface material is. If it's got insulation behind it, then that's more considered a wall. But if it does not have insulation behind it, then it would be fenestration. In terms of how the ratings are determined, we'll talk about both the U-Factor and the solar heat gain coefficient. So for U-Factors, mandatory provision in Section 5.8.2.4 is that the U-factors be determined in accordance with NFRC 100. NFRC is the National Fenestration Rating Council. And also for skylights, that they need to be determined at a slope of 20 degrees above the horizontal, so it's more representative of the actual installation. When we talk about NFRC 100, be aware that these ratings are for the overall product. It's the glass and the sash and the frame. So it's not just the center of glass. And this is an important factor because heat loss through some of the framing materials, particularly metal, is very high. And you can have a product where the center of glass U-factor might be 0.29 or 0.30 if you've got double with a very good low emissivity coating. But when you put that in a metal frame, you could have an overall assembly U-factor of 0.6. So it's important to know that it includes the entire product, and that the factors are higher for products on a slope, perhaps 20% higher. I wanted to touch on a few things in NFRC 100. It was first published in 1991, so that's 16 years ago. And the U.S. passed an Energy Policy Act in 1992, and it required the development of a national window fenestration energy rating system. It specified NFRC as the preferred developer of that, saying that if NFRC didn't develop it, then the U.S. Department of Energy would develop such a system. Well, NFRC went ahead and developed that, and the Department of Energy has certified that it complies with the EPAC criteria. NFRC 100 specifies standard rating conditions, so inside temperature, outside temperature, wind speed, and it's also got standard rating sizes, so you'll have an apples-to-apples comparison. This is similar to what you've got, for example, for furnaces and heat pumps. So there's a national standard about how they're rated. We know that that equipment will perform differently if it's in Miami versus Minnesota, but there's a standard for comparison purposes. NFRC 100 includes all product types. It's included glazed wall systems, curtain walls, and storefronts since the beginning in 1991. Slope glazing like you might see in an atrium, skylights, typical operable windows, casements, awnings, sliders, includes swinging doors, sliding doors. The ratings that you get out of the system are based on simulation, not on testing. So if you're used to doing testing or thinking about testing for structural or for air leakage and water leakage, for U-Factor and SHGC, it's based on simulations, though there is some limited testing that's done for validation. For further information here, you can refer to the NFRC website at nfrc.org. Now the solar heat gain coefficient, that's specified in the next section, 5.8.2.5. And here it's to be determined in accordance with NFRC 200. I'll point out two exceptions. There is an exception that allows you to use shading coefficient for the center of the glass multiplied by 0.86, provided that the shading coefficient is from a spectral data file determined in accordance with NFRC 300. Most of the glass manufacturers have worked with NFRC. They have the spectral data information, and it is included in the spectral data file. There's also an exception B, which allows you to use the solar heat gain coefficient for the center of the glass. Now you can't do this for U-Factor, but it allows it for solar heat gain coefficient instead of the overall product. But I want to point out to you that this will not give you full credit as if you'd gotten the rating for the overall product. So the solar heat gain coefficient for the frame is not 0. It's 0 for visible transmittance. No light goes through the frame, but some heat does go through the frame. The values range from 0.11 to 0.14 for metal frames, and from 0.02 to 0.07 for wood, vinyl, or fiberglass frames, according to the ASHRAE Handbook of Fundamentals. So given that, the solar heat gain coefficient for the frame is almost always lower than that for the glass, so you do get benefit if you get the rating for the overall product. The last rating criteria is visible light transmittance in section 5.8.2.6, also required to be determined in accordance with NFRC 200. Now this is not often going to come up, and it won't come up in the prescriptive approach. It's only necessary if you use the EnvStd, the performance approach, in section 5.6. However, as a practical matter, NFRC requires that products be rated for visible light as well as the U-Factor and SHGC. So information will be available. And as designers, you're obviously going to be thinking about that. You're thinking about the daylighting going into the space. And be aware you can find some pretty good products now with the visible transmittance that's more than twice as high as the solar heat gain coefficient. Much better than bronze or clear glass, where the visible transmittance can be even lower than the solar heat gain coefficient. In terms of the ratings, Section 5.8.2.1 indicates that they have to be determined by a laboratory accredited by a nationally recognized accreditation organization, such as the National Fenestration Rating Council. So what we're looking for here is some independence. The ratings are done by a qualified independent party, which doesn't mean that it's not good to use the software. And the software can be downloaded from NFRC websites. It's helpful for designers to get a sense of what type of products you might need to specify. Manufacturers use it all the time for product design. It's much easier than putting together a prototype and having that tested. You can check out a lot of things by working with variants in the software. There are some limited default values, some U-factors in Appendices A 8.1 and 8.2 for unlabeled products, but they're pretty limited. You're really going to want to get the NFRC ratings. In terms of labeling, there's a requirement in sections 5.8.2.2 and 2.3 for either a permanent nameplate or some other certification of the U-factor or solar heat gain coefficient. The NFRC labels, there are two types. There's one that's put on manufactured products at the factory. This is a 4-inch by 4-inch label. And then for site-built products, there's an 8.5 by 11 label certificate. And let me show you what those take a look like. The label itself, the 4x4 label, in the upper left-hand corner has the NFRC logo. The upper right-hand corner has the manufacturer's name, some description of the product. For example, this is vinyl-clad wood frame. Double glazing, it's got argon gas fill between the panes, it's got a low emissivity coating on the glass, and the product type's a vertical slider. Here are the ratings. You see the U-factor 0.35, the solar heat gain coefficient to the right of that 0.32, the visible transmittance 0.51. Now the label certificate, the 8.5 by 11 document, has the same 4x4 label in the upper right-hand corner. It then has additional information about the address of the product, what the type of product is that's installed, how many of those are in this particular building project, and then the frame material supplier, the glazing material supplier, and the glazing contractor. Down at the bottom, there's a place where the independent inspection agency signs that they've approved on the certification authorization. So this is not something the manufacturer or the glazing contractor completes. This is signed off by the independent inspection agency. Now for the calculation methodology, you calculate the wall areas and the roof areas separately. You also have to calculate them separately for each space conditioning category if you've got multiple types within a building project. So for example, if you've got 6 floors of residential over a street level retail, you'd calculate the street level retail separately from the residential above that. Once you're within those categories, you can do area weighted averaging for the U-factor and solar heat gain coefficient. So some products could have a slightly higher U-factor, some lower, as long as the area weighted average complies with the requirements. Looking at the definitions in section 3.2, the fenestration area is the total area measured using rough opening, including, again, the glass, sash, and the frame. If the glazed area is less than 50% of the door area for doors, then it's the vision area. For all other doors, it's the door area. So again, rough opening, not the glass area. There are 2 types of fenestration: vertical glazing, which is everything that's not a skylight, and skylights. And skylights are fenestration that have a slope of less than 60 degrees, and this is measured up from the horizontal plane. So anything else, even if it's on the roof, is considered vertical fenestration. So for example, you'll have clear stories or roof monitors. It doesn't matter that they're above the ceiling, it's the angle that they're installed at. Now let's go into some of the prescriptive criteria. So for fenestration area, for vertical fenestration, the area is limited to 50% of the gross wall area. And for skylights, it's limited to 5% of the gross roof area. Now remember, these are prescriptive limitations. You can go to the performance approach if you have larger areas and do some trade-offs to compensate for larger window areas. In terms of the criteria for 2004, there is this 50% maximum. And the way that's been established, there's a set of packages that go up to 40%, and then the 50% package is an equal energy package that's a pre-calculated trade-off. For 2007, the standard is going to move back to the straight 40% and not do that pre-calculated package. There is an exception here for vertical fenestration that allows, if it's the street side of street level retail, you can have up to 75% of that area in glazing, provided it's got an overhang that's half as wide as the glass is high. So again, it's the street side, street level only. So it's not upper floors, and it's not any windows in the back of the building or along the alley. This is meant more for visual display so that people can see products as they're walking down the street. Now the criteria for U-Factor is in section 5.5.4.3. Two categories for vertical glazing. There's a fixed category, which includes curtain wall, and an operable category. And I'm going to talk about the U-Factor requirements here. For 2004, there's one set of criteria regardless of frame material, and the value I'm going to cite is for the window area less than 40% of the wall. And here the U-Factor is 0.57. You'll see in 2007 the category is going to split in a different way. So if it's metal framing, the U-Factor requirement for a curtain wall would be 0.45. If it's other framing, wood, vinyl, or fiberglass, it would be 0.35. For operable windows for 2004, you see the U-Factor is 0.67. It's a higher number in particular because the additional metal frame in the sash will result in greater heat loss. For 2007, it's 0.55 for metal frame and 0.35 for wood, vinyl, or fiberglass. To achieve these values for 2004, it's typically double glazing with a very good low emissivity coating. So you probably don't need argon gas or a low conductance spacer, and it could be in most frame types. For 2007, though, to achieve these values, you're going to need a thermal break in the frame if it's metal, or again using the wood, vinyl, or fiberglass frame. For the solar heat gain coefficient for vertical fenestration, two different categories. One for the north, where you don't really see as much sun, so the criteria are less stringent, and then another for the other orientations. So here the criteria varies by the window area. For the 30 to 40% window area, the maximum solar heat gain coefficient is 0.49. You see in 2007 it'll be the same for all areas, and it's going down to 0.40 for climate zone 5. For other orientations in 2004, the solar heat gain coefficient is 0.39, and for 2007, 0.40. So it's going to be roughly the same when it shifts over to 2007 in terms of solar heat gain coefficient. And there is an exception here too. You can take partial credit for overhangs that shade the glass. So you don't need to achieve the solar heat gain coefficient simply within the glass. If you've got a permanent projection that will last as long as the building, you can take some credit for that. And moving on to the next categories, skylights, section 5543, two general categories, either with a curb or without a curb. And here are the key points to be aware of. The U-Factors are all measured based on the rough opening. So the skylights that are built up on curbs, they can actually have a surface area that's double the rough opening area once you consider all the curb that's around that 2x4 or 4x4 foot skylight. So the U-Factor, if it's got a curb for 2004, 1.17. If it's a glass skylight, 1.10. If it's a plastic skylight, that's still double glazing, even though those values are high. For skylight materials without curb, the U-factor you see is much lower, this 0.69. This is more what you would see in an atrium, where essentially you're talking about slope glazing. It's a similar double with low E, but it's a higher U-factor because you've got the higher heat loss due to the slope. The solar heat gain coefficient for the skylights, 0.39 if it's glass on a curb, or 0.62 if it's a plastic skylight, a dome skylight on a curb, so a higher value. And the reason for that is that you can put these low E coatings on glass, but the technology is not there to put it on plastic yet. So it's tougher to achieve the solar heat gain coefficient criteria. If it's without a curb, it's the same as with a curb in terms of solar heat gain coefficient. I will mention that for 2010, the Standard 90.1 committee is looking into possible requirements for skylights with some automatic controls to control lighting in the daylight zone. That was the prescriptive criteria. Let me talk for a moment about the trade-off options here. Trade-off option is in section 5.6. Gives you more flexibility. It's an option you might want to use if you have large fenestration areas, but it does require more work. You have to do a lot of inputs into the program. It's limited to the envelope components, so it does not incorporate lighting or HVAC trade-offs. If you want to incorporate those, you need to go to Chapter 11 to the energy cost budget approach. However, this calculation methodology does include daylighting potential. So you need to have windows with good visible transmittance. If you have glass that doesn't have good visible transmittance, you're going to find you're being penalized, and it's going to be tougher to do the trade-off. As I mentioned in the beginning, the methodology and the assumptions are listed in Appendix C. Again, you don't need to worry about those. They're already incorporated in the EnvStd software. And for directions on how to use that software, see the user's manual. So that's a quick overview of the prescriptive and the trade-off and the mandatory provisions in 90.1/2004. But this is not really the last word on energy efficiency. As you know, Standard 90.1, it's the baseline for energy codes throughout the United States as established in the Energy Policy Act. That means that this is the worst building that you're allowed to build legally in the United States. So these are not highest energy efficiency. This is the worst one you can build legally. In terms of looking ahead and working on green buildings, and we hope you're all working on greener buildings, the next version of Standard 90.1, the 2007 version, will have some increased insulation requirements, better fenestration requirements, and I've highlighted some of those for you. And that should be published later this summer. Another document that goes even further, though, is Draft Standard 189, which is being developed by ASHRAE and IESNA in cooperation and coordination with the U.S. Green Building Council. And this is the design for high-performance green buildings. This document is out for public review right now. You can download it from the ASHRAE website, and it'll be out for public review through July 9th. Here the goal is to achieve 30% additional energy savings. So in addition to the better insulation in windows, it also addresses the fenestration orientation and exterior shading. And to give you a sense of what sort of options are out there, I've got a couple of projects to show you. Here's a picture of a building. It's a 48-story hotel and condominium with a 3-layer glazing system that has a U-factor of 0.21. So this is something that's actually 3 times as good as the criteria for the 2004 version and more than twice as good as the criteria for the 2007 version of Standard 90.1. And people might ask, well, U-factor, aren't these buildings usually being cooled all the time? Well, as it turns out, a lot of these buildings are in bimodal operation. So it's a situation where then when they're occupied, which is what most people think about, yes, the people are there, the lights are on, the equipment's are on, there's lots of heat, and so you're really concerned about the solar heat gain coefficient. But buildings are actually unoccupied more than they're occupied. And so in those cases, they're losing heat. So you want to make sure that they have good U-factors, good insulation to offset the heating load. Again, you don't usually think about it, but the morning warm-up from 5 to 7 a.m. is when a lot of the heating energy consumption is used. And there's no lights, there's no people, there's no equipment on, but everybody wants it up to 70 by the time they get into the building. One other example here is this 19-story office building, 250,000 square feet. This has a 4-layer glazing system with a U-Factor of 0.14. So there's different technologies out there that you can use and are being used, and also some other innovative technologies being developed to get to your really high-performance green building. That's about the conclusion of our presentation today. If you want further information, you can refer to the ASHRAE website, pick up a copy of the standard, the user's manual, and more information on training opportunities. And certainly refer to the www.energycodes.gov for other standard and compliance tools.